In this video, we're going to talk about conservation of energy shortcuts. So first, let's remember from our last video a bit about what the conservation of energy is. It starts with Aristotle, the Greek philosopher, who taught that everything is a mix of what it actually is and potentially will be.
Still Snoop Dogg and D.I.
So physicists use this to understand potential energy, and we say that potential energy is potentially kinetic energy. So think of a roller coaster car on top of a hill. That roller coaster car has potentially kinetic energy, meaning at the bottom of the hill it can have kinetic energy if some force pulls it down the hill. Now, we also say that potential energy comes from conservative forces, like the force of gravity. Here's what I mean. Conservative forces are forces that conserve energy. So if I have a little bar graph here of the kinetic energy and the potential energy of a ball when it is thrown up, we'll notice that the force of gravity first decreases the kinetic energy, but it doesn't lose it, so we store it as potential, and then it gets turned back into kinetic energy. So again, the force of gravity slows the ball down, and we say that that energy isn't lost, it's stored in a potential energy. Now, that means for us, at any time there is a total energy that is made up of the amount of kinetic energy an object actually has and its potential energy. That potentially can be kinetic energy later. We say that this total mechanical energy is always the same, or the energy in the beginning is equal to the energy at the end. Now, for our example of a roller coaster on a hill that's at a height of h, let's say you have initially 100 joules of energy, and you know that the roller coaster starts with an initial velocity of 0. So I can tell from this information a couple of things. First of all, that the kinetic energy in the beginning has to be 0 since the velocity is 0. And the total of k and ug, the kinetic and potential, has to be 100. So the potential energy is 100 joules since I know those two numbers have to add up to the total of 100. Okay, well, halfway down the hill, the potential energy deals directly with the height, and at half the height, you would have half the potential energy, so 50 joules. And the kinetic energy would therefore have to be 50 joules as well, so that they both add up to 100. At the bottom of the hill, you're at a height of 0, so your potential energy due to gravity is 0, and therefore your kinetic is 100, so that the two add up to a total of 100 joules of energy. Well, now let's talk about our first shortcut. Imagine that you're dealing with a situation where you go underground. So here we have a roller coaster. Draw this for yourself so that you can get a good example. And this roller coaster is actually going to go below the ground level of 0, then through a loop and eventually wind up over here somewhere where it's at the ground that it started from. So let's talk about the effect that this has on potential and kinetic energies. Same situation, 100 joules in the beginning, and so that's going to be the total throughout, and it starts from rest. So I know that the kinetic energy is 0, and therefore the potential is 100, so that my total is 100. At half the height, I'm going to have a potential of 50 joules and a kinetic of 50 joules, so that the total is 100. And at 0, you guessed it, I'm going to have no potential energy, because I'm at a height of 0, and a kinetic energy of 100, so that those two add up to 0. Now here's where things get a little bit conceptual and tricky. What happens when I go below ground at a negative height of h over 2? So, half the original height, but underground. Well, now this means that I'm going to have a negative height, and therefore a negative potential energy of 50 joules, similar to what you had at a positive height of h over 2. You can have negative heights because the ground is a relative concept. You can be above ground or below ground. So my potential energy relative to that 0 is at a negative. What does this mean for the kinetic energy? Well, it means that the kinetic energy is going to be a number that when added to negative 50 gives me 100. So the kinetic energy is a positive 150. Because when I add 150 to negative 50, then I'm going to get a total of 100 joules of energy. Okay, so now as the car goes along the track, it's going to have these different amounts of potential and kinetic. When it gets to this height right here, it'll have 0 joules of potential and 100 of kinetic. Then at the top of the loop, it's going to have 50, 50. And at the middle of the loop again, it comes back to that 0 potential, 100 joules of kinetic, comes back to the ground, negative 50 joules of potential energy, 150 of kinetic, and then eventually up to 0 again, where it has 0 joules of potential and 100 joules of kinetic. Now, I just showed you these different stations so that you can get the idea that the total energy is always conserved. It adds up. And usually what we're trying to do is we're looking at the potential energy and the kinetic energy with these specific equations because there's something that we want to use the potential or kinetic energy to find. Normally, we're looking for the velocity of an object at a certain spot. Sometimes we're trying to find the height. Okay, so what's the trick here? How does it work? Well, we're going to take advantage of this underground fact and use it so that we're being really smart and clever. We're going to choose the ground. So again, the potential energy depends on height. And height is a relative concept. So the fact that it only depends on height, well, first I should say this, we call this path independence. It means it doesn't matter if you're going down a straight incline or a curvy ramp or a really wild path. The only thing that affects the potential energy due to gravity is the height. So we're always looking at the height. So the trick is we choose where the ground is, which means when we say that a height is at 0, then there is no potential energy there at that height. Okay, let's see how this trick plays out in an example problem. Here we have a situation where a roller coaster car is going down a hill and through a loop. We want to know what is the speed of the car at the top of the loop. Okay, so first let me solve this problem traditionally, right? Let me go through it really normal. I'm not going to use the trick. I'm just going to try and answer it at face value. Well, I would look at the energy in the beginning, E naught, and know that it is equal to the energy at the end. So in the beginning, I'm going to have some mix of kinetic and potential, K naught and Yu-Gi-Oh. Then at the end, I'm going to have some mix of kinetic and potential. And remember that at any point, the potential is going to be mgy, and the kinetic is half the mass times velocity squared. I'll put that up there just as a reference. Okay, so what's the kinetic energy in the beginning? Well, there is no velocity, so therefore there is no kinetic energy in the beginning. What about the potential energy? Well, I'm going to need to use this equation to find it. And my initial height is 10 meters, so I would do the mass, 60 kilograms, times the acceleration due to gravity, 10 meters per second squared, times a height of 10 meters. So this gives me 6,000 joules of energy. Okay, so what does that tell me? Well, that tells me that 0 plus 6,000, that's the total energy. Right? It's going to be 6,000 joules no matter where I'm at. And I know that whatever these two numbers are, they have to add up to 6,000 joules. So let's figure out that number. The 6 meter height that you're at here, I can use that to find the potential energy. I can use the mass, 60 kilograms, times the acceleration due to gravity, 10 meters per second squared, times that 6 meters of height. Okay, and here I'm going to find that I get 3,600 joules of potential energy. So what can I do with this? Well, now I know how to find the amount of kinetic energy. It's going to be that total 6,000 joules minus 3,600, because I know that they both have to add up to 6,000. So 6,000 minus 3,600 is 2,400. And if you're like, wait, what? 2,400 plus 3,600 is 6,000. That's the idea. The total energy is conserved. Okay, cool. Well, what am I trying to do with this information? Well, again, we want to find the speed of the car at the top of the loop, and that means I need to know the kinetic energy so I can use this equation to find the speed. Now that I know the kinetic energy, I can find the velocity, right? I'll do that up here. I know that K equals half the mass times velocity squared, and if I solve for the velocity, I multiply both sides by 2 to get rid of the 1/2. Then I divide by the mass, so that it goes away, And I have v squared equals 2 times the kinetic over the mass, so I have to take the square root. And this will tell me that the velocity is equal to the square root of 2 times the kinetic energy over the mass. Let me solve that up here. 2 times the kinetic energy, which is 2,400 joules, over the mass of 60 kilograms. Okay, so what do I get? 8.94, we'll say 8.9 meters per second. Okay, good. So this was the traditional way. This is sort of the long way to solve this problem. Is there some way for us to get to this answer more quickly? Well, yeah, there is. So instead of starting by looking at the energies in the beginning and the energies at the end, there was this trick that I could have done to make things a lot faster. Let me get rid of all of this work for the kinetic and the potential energy here to show you the trick. So the shortcut here is to choose the ground. If I decided that this is the ground, that 6 meters isn't 6 meters, it's 0 meters, then that means I don't start at 10, I start at 4. Right? Because 10 meters is 4 meters above 6, so I'm starting at a height of 4 meters instead of 10. What does that do for me? Well, in the beginning, I still have a kinetic energy of 0 because I'm at rest. And when I calculate Yu-Gi-Oh, I'm going to get a different number. So 60 kilograms times 10 meters per second squared times 4 meters. This is going to give me 2,400 joules. Interesting. That number seems familiar. Okay, well now when I move to the end, I know that the potential energy now, I don't have to calculate it. I've said that it's at a height of 0. It's at the ground. So that means that mgy is really mg times 0, or I have no potential energy. Wait a minute. If I have no potential energy, then it's really obvious. I know that my kinetic has to be 2,400 joules, right? Because that's what the total in the beginning and the end is. Oh, that makes a lot of sense. And this is the same kinetic energy that we use in our velocity equation, and we're going to get this same speed. So that's the trick. That's the first shortcut. You can decide where 0 is. And where 0 is, there will be no potential energy due to gravity. And that typically can shorten your problem-solving process, because you know that at some point you're going to have kinetic energy, and at another you'll have potential energy. Okay, great job. So what's the next shortcut? Well, energy analysis can be done without mass. Remember, we're saying that the energy in the beginning always equals the energy at the end, and that means I'm going to have some combination of potential energy plus kinetic energy in the beginning, and then potential energy and kinetic energy at the end. And I know that each potential energy is going to depend on mgy, and the kinetic energy is mv squared. So if I do that for the beginning and the end, I've got knots and then not knots like mgy. Okay, so if I write it all out, every term has m in it. There is a mass in every term. So that means when it comes to mechanical energies, kinetic and potentials, I can actually get rid of m. Let's see how this works in a problem. Harry Frobos. I'm sure I'm saying that wrong. So Harry Frobos is a famous stuntman from the silent film era who would do really large drops into water, typically with a horse that was also dropping with him. Like this horse is actually falling down. Pretty cruel. Anyway, in 1936, Harry Frobos jumped into the ocean from the airship Graf Hindenburg, you know, the thing that caught on fire, which was 120 meters above the water's surface. What was his velocity before he hit the water? And obviously, we're going to ignore air resistance. Okay. So, how do I solve this problem? Well, here's the Graf Hindenburg, and here's Harry Frobos. Yay! Okay. And then the water. Initially, Harry Frobos, why not, is at a height of 120 meters. Then when he hits the ground, he's at a height of 0. Or when he hits the water, we'll say that that's where the ground is. Okay, so how do I find his velocity? Well, I don't know the mass. I don't know the mass of Harry Frobos at this exact moment, but it doesn't matter if I'm clever. I know that the energy in the beginning is equal to the energy at the end. So before I even get started, I'm going to think, what kind of energy does he have in the beginning? What kind of energy does he have at the end? In the beginning, he could have potential energy due to gravity or kinetic energy. And at the end, he could have potential energy due to gravity or kinetic energy. So what does he have? Well, if he initially just drops, that's what we're assuming, then we know his initial velocity, v0, is 0. And therefore, there is no kinetic energy in the beginning. And when he hits the ground, or the water, it's a great picture, he's at a height of 0, which means the potential energy will be gone, 0. Or the potential energy that he has in the beginning is going to turn into all kinetic energy at the end. Well, I don't know how to calculate the potential energy in the beginning because I don't know his mass, and I need to know the mass to get a number. Well, let's plug in our equations first before we go number crazy. So Yu-Gi-Oh is really mg y naught. And k is really 1/2 m v squared, where that v is what we want to find, right? That's his velocity that he has right before he hits the water. Right away, you should see this awesome shortcut. There's an m on both sides of the equation, which means that we can cancel it out. And now I know that gy naught is equal to 1/2 v squared. And I can solve for v squared. I multiply both sides by 2 to get rid of the 1/2, and then I take the square root. And suddenly I know that the velocity is equal to the square root of 2 times the acceleration due to gravity times the initial height. So the velocity is the square root of 210 meters per second squared times the initial height, 120 meters. So the square root of 2 times 10 times 120 is 48.98, so we'll say 49 meters per second squared. Not squared, sorry, just meters per second. Okay, so in this problem, we were able to get rid of the mass, and that really helped us out. Now let's do a problem that uses both tricks. Stuntmen are great, and eventually in history, we get to the greatest stuntman of all, Rod Kimball. Rod Kimball rides his moped down a steep hill. The hill is 80 meters high, and Rod starts from rest. At the bottom of the hill, Rod goes up a ramp that is 10 meters tall. What is Rod's speed right as he goes off the ramp? Well, let's kind of draw this, hill and then ramp. And I know that initially there is a height of 80 meters, and then at the ramp's height, you're at 10 meters. Rod is on a bike. Drawing bikes stick figure style is hard. Ooh, yay. And then when he goes off the ramp, I really should take a drawing class. We want to figure out what's his speed. Oh, and the initial velocity is 0. Okay, so how do I solve this problem? Well, the first thing that I should do is realize that I can apply the shortcut. If I say that he leaves the height of the ramp at 0, then he's actually on a hill of 70 meters. Okay, make sure that that collects. I've just reduced both things by 10. Okay, so now I've chosen my ground. What does this mean for me? Well, this means when I think about the energy in the beginning and the energy at the end. In the beginning, he will not have any kinetic energy because he starts at rest. He will only have potential energy due to gravity, Yu-Gi-Oh. And at the end, if I've decided that he's at a height of 0, then he doesn't have any potential energy due to gravity because his height is 0. He'll only have kinetic energy. Man, we are crazy smart. Now I just fill in my equations. mg y naught equals 1/2 mv squared. And boom, the second shortcut. I can get rid of Rod Kimball's mass. And now I know that gy naught equals 1/2 v squared, and the same thing as last time, multiply both sides by 2 to get rid of the 1/2, and then take the square root to get rid of the v squared. And now the velocity is the square root of 2g(y)0, where I'm careful not to use 80, and instead I'm using 70. 2 times 10 meters per, not meters, yeah, meters per second squared. I'm losing my mind. Times 70 meters. Okay, so the square root of 2 times 10 times 70 meters is 37.4 meters per second. Okay, congratulations. So in this video, you learned 2 shortcuts. One, how to change the heights so that you are choosing a ground or 0 at a very special and important place. The other is the ability to do this energy analysis with your equations first so that you can get rid of the mass in order to solve for problems where you don't know the mass of the object. You are super smart and awesome, and I'm so proud of you. This video is done.